Hi, in this lecture I'm going to go over angular kinematics. You remember the term kinematics from the normal linear kinematics. The kinematics was essentially a study of the relationships between concepts such as velocity, position, acceleration, both in one and in more dimensions, and everything that followed, all the results, all the so-called, say, kinematical equations, they just followed from the definitions. And at all times we were just describing motion. We were never actually, say, explaining why something moved. That came in when we talked about forces. Now, in terms of rotational motion, we've already talked about torque, right? That's sort of an analogous quantity to force. But now we're going to talk about angular kinematics, namely angular position, velocity, and angular acceleration. So we need to figure out what is the basic unit. In normal linear velocity and linear kinematics, we had, say, the meter and the second. Now, when we have rotational kinematics, we're talking about essentially moving in a circle, or an object rotating, and rotation of an object you can think of as each point on the object moving in its own circle. So, the basic unit of angle is the radian. Now you might think, what about degrees? Sure, you can use degrees, but the radian is mathematically a lot more convenient. Now, what is 1 radian? So if I imagine I draw a sort of circle with a pizza slice like this, then I can call the distance around it S. This is my arc length. And the angle, this is the radius, the angle is 1 radian. Angle is 1 radian if, and only if, I'm not going to write it though, if the arc length is exactly equal to the radius. That is the definition of 1 radian. Hopefully you remember that from your math courses or your previous physics courses, but I think it's worth emphasizing right here. So what does it imply? Suppose I have some other angle. Maybe I care about this angle here. Or no, well, how many radians is this? Well, the radius is the same no matter what. And I can go around the edge here. I ask, well, how long is this? Let's just say, I'm eyeballing it, it's 2.5 radii. All the way around, all the way from here to here, along the edge. 2.5 radii, well, then this would be 2.5 radians, right? It's in the name. So the radian, or more generally the notion of angle, is defined as a ratio of this length to the radius. And notice that if I scale up my circle, I make it bigger, I might make r bigger, but I also make the arc length bigger by the same amount. So the size of the circle does not actually make a difference. So we define angle. Have you ever defined angle before? I'm not sure. What do we mean by an angle? Is the ratio of arc length divided by radius. Or I can rewrite that as S, the arc length, the distance around, is the angle times r. And that is essentially part of why using radians is a lot more useful than degrees, because with degrees I constantly have this factor of like 360 over 2 pi flying around. It would just become messy. So radians is a very sensible unit to use. Now, usually the convention is, well, where do I start, right? What's my coordinate system here? Well, this is the center of my circle, but where is 0 degrees? I can say x is 0 here, and this is the positive direction. What's the equivalent thing to do for a circle? So the convention is, and this is not always the case, right? It doesn't always have to be done, but more often than not, we say this is theta equals 0, and then this direction, counterclockwise, is the, let me write it out, positive theta. So if I have a negative theta, I'd be down here, positive theta this way. Of course, I can go all the way around, right? When I get to 2 pi, I'm again where I started. But if I say talk about a change in angle by how much has the object rotated, then there's a difference between having rotated once all the way around and just staying the same spot, even if in both cases you end up in the same position again. So it matters whether I'm saying theta is 2 pi or theta is 0. It means different things if it's a change in position that I'm talking about. So in one case, if delta theta, say, the change in angle is 2 pi, it means the thing has rotated once all the way around. If the change in angle is 0, it means we've just been sitting there the whole time. Okay. So let's define then the rate of spinning. So rate of rotation, we're going to call this the angular velocity. And we're giving it a symbol omega. It's a lowercase omega, right? I'll just write here. You have met omega before in the context of, say, electrical resistance. The ohm had this omega symbol, but it's a capital omega, right? We don't want this here. We use the lowercase omega. That's essentially the same thing, not the same thing, but the analogous quantity as the v, the velocity in standard linear kinematics. And omega could be positive or negative. Positive in this case would mean going counterclockwise. Negative would mean going clockwise. Although you are of course free to define your directions differently, but this is it's a convention. Okay, now how is it defined? Well, we're going to say omega is equal to the rate of, the rate of change of angle with respect to time. Right? The same way that v, I'm going to write this out over here, CF, Latin conferatur, it means to be compared with, common abbreviation in academic writing. CF v is dx dt. Now you might say, hold on, isn't there also like a y and a z, maybe different directions? Are there different directions of rotating? I only see this way, or maybe this way. Well, there are other directions. For example, the object could rotate like this way. Right now it's just spinning on the spot, but it could be going this way. It could also be sort of rotating like this. Right, so there are 3 directions of rotation, and we'll come back to how to think about those in more detail in the near future. But for now, we're essentially doing one-dimensional angular kinematics. Right, so d theta dt, there's only one angle here to think about. Now, of course, we might have a very simple situation where this is just a constant, right? The angle is changing at a constant rate. So we're going to do an example of that in a second. Before we do, let me just very quickly define 2 other quantities that you're going to come across. Other relevant quantities, things you might meet out in the field, out solving problems. One is the frequency, usually written as f, and that is the number of rotations per second. Of course, the units of omega, right, is radians per second, angle per time. Frequency f tends to be given in number of rotations, full rotations per second. So how many rotations per second, and because I have 2 pi radians in one rotation, I can relate this directly to omega. I'm going to get that 2 pi times f is equal to omega, right? Because if, say, let's visualize this. Why is it 2 pi here, not over there? I mean, if f is 1, right, 1 time per second this thing goes round, well, then omega would be 2 pi radians per second. If f is 3, the thing spins around 3 times per second, well, then it would be 2 pi plus 2 pi plus 2 pi radians per second. So you can check that this is the right way round to combine those, the 2 pi is on the correct side, just by thinking through 1 or 2 examples that you can directly visualize. That's a little trick that often helps if you get confused. Oh, do I divide by 2 pi? Do I multiply 2 pi? How do I even know? Just plug in some simple examples in your head and think what the answer should be, where you can visualize it easily. The other quantity you're going to come across if you talk about rotations is the period, usually given this capital T symbol. Don't confuse it with tension if you've got a problem that involves both. Right, you can call it anything else, but that is the convention. And that's the time per rotation. It's kind of the inverse of frequency. In fact, that's exactly what it is. F is 1 over t. Let's make sense of this. If I go around once a second, then the time it takes is 1. 1 over 1 is 1. That makes sense. If I go around 3 times per second, f is 3, then it should be a third of a second to go around. If f is 3, then yes, t would be 1/3. Right? So again, you can check that this makes sense just by trying some very simple numbers where you can visualize the motion. Let's do an example. So here's the example I want to go through. Find the angular velocity omega of the Earth going around the Sun. Then find the Earth's speed. Alright, so where do we start? What do we know? Well, what we know about the motion of the Earth around the Sun is how long it takes to go once round. A year, right? So we know the period t is 1 year. Now you can convert that to seconds. 365 and a quarter, including leap years here, like the average here. 365 and a quarter times 24 hours. So we put days in a year, hours in a day, times 60 minutes an hour, times 60 seconds in a minute. What you're going to get is about 3.154 times 10 to the 7, about a bit over 31 million seconds. Now there's a trick. If you just want a rough estimate, like a very rough estimate, like 2 significant figures, well, it's 3.15, call 3.14. It's essentially almost pi times 10 to the 7. I mean, it's not, right? But it's a sort of funny way to remember it. The year has pi times 10 to the 7 seconds. There's no conspiracy, no mathematical anything, it's just a coincidence, right? That this number is fairly close to the numerical value of pi. Of course, it's not super accurate. This is to 4 significant figures slightly better. But as a party trick, pi times 10 to the 7. Alright, so we've got the period of the Earth to go around the Sun once. It's a big circle, roughly, circular motion. So now we can find the frequency. Frequency f, that's 1 over t. So 1 over 3.154 times 10 to the 7. You do the math. I cheated and I did it before recording this lecture. It comes to about 3.17 times 10 to the minus 8 rotations per second. So it's a very tiny part of a rotation. 0.000000317 rotations per second. So that means we can then find omega, which is 2 pi f. How many radians per second? Well, this number times 2 pi. I'm going to plug it in. Right, I'm going to plug this in here, and I'm going to get 1.99 times 10 to the minus 7 radians per second. And I am done with the first part. I found the angular velocity of the Earth going around the Sun. Now to find the speed, right, I'm going to use the fact that speed is the distance traveled per time, so I can write this as ds, the arc length, per time, which is nothing but d dt. What is s? S is r times the angle. Remember we talked about this near the beginning when we understood what a radian was, so we're just taking the time derivative of this, but because the radius does not change, this is r d theta dt, or r times omega. A very important relation that the speed of a point going in a circle is the radius times the angular velocity. It just follows from the definition of radian, of course, as displayed here. So what is r? Now this is something we have to look up. The orbital radius of the Earth is about 150 million kilometers. Orbital radius of Earth is about 150, how many zeros? That many zeros, kilometers. 150 million. So 100, maybe I'll just leave this in kilometers and I'm gonna get my speed in kilometers. So this times this means the speed is equal to 150 million times this quantity here, 0.000000199 times 10 to the minus 7. You do the math, a lot of zeros are going to cancel out, and we are going to get, I did work this out too, actually it's something that's fairly well known, it's about 30 kilometers per second, just short of 30 kilometers a second. It's the speed of the Earth in its orbit. Alright, so now let's move on and introduce angular acceleration. Now we're going to go to scenarios where omega, the angular velocity, does not stay constant. So let me start a new page for that. Here's the definition of angular acceleration. It's usually given the symbol alpha. Right, so this the Greek lowercase a, looks a bit like an A that's with a fish tail, I guess. And it's defined as the rate of change of the angular velocity with respect to time. Exactly analogous to the acceleration being dv dt, the rate of change of velocity with time. So suppose then, for example, alpha is constant. So that means your rotating object is increasing its rate of rotation at a constant rate. Right? The same way acceleration means increasing your velocity or decreasing your velocity at a constant rate. So if a is constant, then we could, for example, find the change in the angular velocity as alpha times the time taken to make that change. And I'm just going to write this down and let you think about it. We want to find a change in angle while my system is speeding up in its rotation, it's increasing its angular velocity. That would be given by your initial angular velocity times the time plus 1/2 alpha delta t squared. Now you look at this and this looks familiar, right? You remember it from normal kinematics where this was a v naught and this was an a and not an alpha, and this was a delta x. And it has to be the same. Maybe you remember how you derived this. You could derive it as essentially integrating a constant alpha twice, or maybe you derived as the area under your VT graph, velocity time graph. There are many ways to get to this, but it has to apply here too, because in the case of velocity and acceleration, the way you knew them, still know them, all that just followed from the definitions, and the definitions here are exactly the same. Omega is defined as the time derivative of angle, the same way v was defined as the time derivative of x. Alpha is defined as the time derivative of omega, the same way a is defined as the time derivative of v. So any result that held for those essentially mathematically holds for this one too. Of course, it has a different meaning, but it still holds. And another thing that you might then know is, oh, if there's a change in my angular velocity, there's some final one. If I square this, it's equal to initial one squared plus 2 alpha times the change in angle. Right? Again, remember the analogous equation v final v initial 2a delta x. Well, that equation just followed from the definitions. That equation followed from this, and you eliminate delta t between them, and you're going to get this. Right? So because all definitions are the same, the mathematical relationships are the same, you're going to get the same other relationships, the same results here. Like, the math doesn't care whether you call this omega or v or what. The mathematical relationships are going to turn out the same. So you have this dictionary almost between those theta quantities and e and x, omega and v, alpha and a. And this dictionary extends a lot further than this. It's ultimately going to include, we already know that it includes, for example, torque is a little bit like force. We're going to meet other concepts such as moment of inertia, rotational kinetic energy, rotational or so-called angular momentum, and they're all going to be exactly analogous to their linear counterparts in terms of how they are related among themselves. And you'll see that. And to some extent it actually demonstrates how much of what we're doing is really just manipulating the math. Alright, there's one additional thing, of course, with angular acceleration and velocities, is that you can then also ask, well, what is the actual speed of something going in a circle? And we had that the arc length is equal to the r times the, let's call it delta theta, the change in angle between 2 points. What's the angle? The angular position change. Well, you take that times r. Before I just wrote theta, that's fine. You have to understand what it means. It doesn't matter what symbol you use. Then we have that the speed is equal to r times omega. This is just taking this and, well, taking the time derivative of this, right? And then, what happens if I take the time derivative of this? I'm going to get r times alpha. Now, you might want to write acceleration, but remember, speed is not velocity. We're just interested in what is our rate of change of speed, and it's the tangential acceleration. So if you're confused right now, let me just draw this quickly. Imagine something's moving along this part of a circle. The object is here. It has some velocity this way, right? Now, its acceleration has 2 components. There's the radial acceleration, because it points along the radius, and there's the tangential acceleration. I guess it's called a subscript t for tangential, like this one here. This one makes us turn, that's always true, the acceleration perpendicular to the direction of motion causes turning without speeding up or slowing down. Acceleration forward or backwards in the same line as the velocity causes speeding up or slowing down. If your actual acceleration vector has both components, well, then you'd be turning and speeding up or slowing down. But this one here, therefore, does not actually change the rate of change of speed. In fact, this one, if you're going in a circle, we're going to call it the radial acceleration. But if you're going in a circle, if circular, then it is the centripetal acceleration. ACC, abbreviation for acceleration down here. Try to squeeze it in right at the edge of the paper. So we only care about this one, which way this is the tangential acceleration. There might be acceleration the other way. In fact, there probably is, because otherwise the thing would go in a straight line, not rotate. If this is the the end point of my pencil is spinning, well, I might be tracking this point here. There better be a force that stops this from going straight. Probably just the internal forces that keep this pencil in one piece. Alright, so let's do an example involving angular acceleration. Here's the example I want to think about. An airplane propeller goes from 0 to 2000 RPM rotations per minute over the course of 14 seconds. Find the angular acceleration and the number of rotations completed by the time it reaches 2000 RPM. So it starts at rest. Here's my propeller. It starts spinning. It's going faster. And at some point, it reaches 2000 rotations per minute. It's a common way to write down what is essentially a frequency or an angular velocity. In rotations per minute, for example, if you have an older hard disk in your computer, like it's not solid state, where these magnetic disks rotate, it might be 7,200 rotations per minute. Or in the engine in a car, the car might tell you as you're driving, you're currently going with 3,000 rotations per minute in the engine. This is the common way that you encounter a lot out there in the field, in daily life. It's a bit of a funny one for us physicists. We say, why not just say radians per second? But, we can deal with it. So let's deal with it. So, let's write down this information symbolically. My initial angular velocity is 0 radians per second. My final angular velocity is, well, I can write it as 2000 rotations per minute. So this is okay to write because I'm making the unit explicit. Right? This is not radians per minute. This is RPM is a unit that means rotations per minute. Because I want to convert that, so I'm going to say it's going to be 2000 times 2 pi. That would be radians per minute, but then divided by 60 because we only want a second, the 60th of a minute. So what does this make? And according to my math, that makes about 210 radians per second. So let's find the angular acceleration. Of course, what we're really going to find is the average angular acceleration over the time period. We don't know for sure if omega goes from 0 to 2000 in a straight line. Maybe after 7 seconds I am not at 1000 but at 1200 because it's easier to get it started than to speed it up further. Who knows, right? But let's go with the question, essentially finding the average angular acceleration. Would have told us otherwise if this were a non-constant angular acceleration. So that's going to be my delta omega divided by delta t, right? I can write deltas instead of d, instead of a derivative, because I know this to be constant. So this is going to be 210, I guess minus 0, write it out once, divided by, how long does it take? 14 seconds. So that many radians per second divided by 14 seconds, that makes 15 radians per second per second per second squared. So you can tell the units also much acceleration the way you know it in meters per second squared, except it's now in radians per second squared. That's the first part of our answer. Now, how far has this propeller turned? You can imagine, if you just visualize, it's going to return, over and over and over around many times, maybe hundreds of times, at least dozens of times, before it's going at full speed. Let's find that. Delta theta is equal to the initial angular velocity times the time plus 1/2 alpha delta t squared. This one here is 0, makes that part go away. And I figured this one out. This was 15 radians per second squared. This one here is 14 seconds, so that gets squared. We do the math, and unless I'm mistaken, we're getting 1470 radians. Now, how often is it around, right? It says what's the number of rotations. So I guess we convert that back into rotations. So we have 1470 divided by 2 pi. So 1470 radians divided by 2 pi, that comes to about 234 full rotations. Now, radians is funny. Now you look at this like, where did the radians go? What happened to my units? It's sort of like the pi itself contains the units of radians per rotation. Like 2 pi, right, is a quantity whose meaning is how many radians is it per rotation. So mathematically, if you want to be rigorous, you can imagine that pi secretly contains the unit radians per rotation. In practice, we might be more inclined to say radians. It's not really a unit, because how was it defined? How were those angles defined? Let's go back to the beginning. A radian, right, was defined as a ratio of sides, meters. So angle really doesn't have any units at all. It's a ratio of lengths. But we write radians, rad, is our unit, it's kind of a fake unit, because it, radians right here, because it's telling us, the reader, that the quantity that you're looking at, this unit-less quantity, is in fact a ratio of lengths. It's a little bit subtle here, but practically speaking, radians isn't really a unit, right? So, understand what your number means. Does it express the angle? Does it express a length, a number of rotations, and so on? Right? Keep track of it. But in terms of dimensional analysis, you have to be very careful if you want to include rad. Like you have to, for example, associate 2 pi with units of radians per rotation. Alright, that in a sense is all there is to it. Right? You can do lots of those problems, but you've essentially practiced the same material when you did kinematics a long time ago. So now the interesting part is going to be to relate these quantities, specifically the angular acceleration, to the torque that's acting on an object and to the properties of an object, in particular a thing called moment of inertia. And that's what we're going to come to next. Thanks for watching.